Hello everyone, today I will be presenting a responsive knapsack-based algorithm for resource provisioning and scheduling of scientific workflows in cloud. Now let's look at the abstract. Scientific workflows describe series of structured activities and computation that arise in scientific problem solving. Scientific workflows are used to process vast amount of data and to conduct large-scale experiments and simulations. They can greatly leverage the ease of access, affordability, and scalability offered by cloud computing. Cloud computing is the practice of using a network of remote servers hosted on the internet to store, manage, and process data rather than a local server or a personal computer. This paper proposes an adaptive resource provisioning and scheduling algorithm for scientific workflows deployed in IaaS clouds addressing their key challenges. Simulation experiments demonstrate that it performs better than other state-of-the-art algorithms. Now let's look at the introduction. Workflows are basically a set of computational tasks and a set of data or control dependencies between them. They are deployed to analyze and process large amounts of data efficiently on distributed platforms, which requires scheduling algorithm for the task. Scheduling algorithms plays a crucial role in running workflows efficiently as they are responsible for the management of the task on the distributed compute resources. The decision of schedule algorithms are made to minimize the total cost or make span while meeting their budget and deadline. The scheduling problem is non-trivial, also referred as an NP-complete problem. Infrastructure as a service, also known as IaaS cloud, provides easily accessible, flexible, and scalable infrastructures for deployment of scientific workflows. IaaS, which is based on the pay-as-you-go model, provides storage services and network infrastructures for data transportation. Key characteristics of cloud that algorithm needs to satisfy: first, static resource model. The key challenges is to determine when to dynamically provision VM on cloud and when to deprovision VM on cloud, along with how many and of what type. Second, utility-based pricing model. There is cost associated with VM, so we need to minimize the cost of execution while meeting deadline. Third, dynamic state of VM and uncertainty of the network. Cloud is not static but dynamic. Also, bandwidth of the cloud may vary. WRPS algorithm schedules scientific workflows in clouds. As a result of this requirement, WRPS algorithm was proposed that schedules workflows on the cloud. It's deadline-driven cost minimization scheduling algorithm. Here, the deadline is given, but we want to minimize the cost of running workflows in cloud by optimizing it. Now let's look at the relative work in this field. Advancement in cloud computing has allowed many dynamic algorithms and made capable of adapting to changes in the environment. Dynamic provisioning, dynamic scheduling, also known as DPDS algorithm, adjusts number of VMs based on application usage. The partial balanced time scheduling algorithm estimates the optimal number of resources needed per billing cycle period so that a deadline is met and the cost is minimized. This approaches focus on the task level optimization strategy, undermining the adaptability to unexpected delays. The static provisioning, static scheduling, also known as SPSS algorithms, are designed to schedule a group of interrelated workflows, which creates a provisioning and scheduling plan before running any task. IaaS Cloud Partial Critical Path, also known as ICPP algorithm, is based on workflows' partial critical paths and tries to minimize the execution time while meeting a deadline constraint. Static algorithms are sensitive to execution delays and runtime estimations of tasks, which is a trade-off for the ability to perform workflow level optimization and compare various solutions before choosing the best suited one. WRPS combines both dynamic and static to balance between adaptability and optimization. Now let's look at the application and resource models. Workflows are modeled as directed acyclic graphs, also known as DAGs. Now DAGs are the graph with directed edges and no cycles or conditional dependency. Workflow W is composed of a set of tasks T, which can be represented as a set of T1, T2 all the way to Tn, and edges Eij. Workflow process data in the form of files. A common approach used to share these files among tasks is to use a peer-to-peer P2P model. While shared storage increases resources utilization and also decreases the least cost of virtual machine. VMs are leased on demand and charged per billing period. VMs are modeled in terms of processing capacity PCVMT and cost per billing period CVMT. The processing time of task T on a VM of type VMTT of type T is defined as the sum of execution time and the time to read input file and write output file to storage. Now let's look at WRPS algorithm. WRPS has dynamic and static features. Its dynamicity lies in the fact that the scheduling decisions are made at runtime. Every time tasks are released into the execution queue, this allows it to adapt to unexpected delays caused by poor estimates or by environmental changes such as performance variation, network congestion, and the VM provisioning delays. The static component expands the ability of the algorithm from making decisions based on a single task to making decisions based on a group of tasks. Main purpose is to find a balance between the dynamic algorithm and the global algorithms. Using pipeline and statically scheduling tasks, we can make better optimization decisions and find better quality schedules. Pipeline is simply a group of tasks with one-to-one relationship. The first task in the pipeline may have more than one parent, but it must only have one child task. Pipeline is associated with the deadline, which is equal to the deadline of the last task in the sequence. The tasks in pipeline are clustered and usually run on the same virtual machine, basically due to two factors. Firstly, the tasks are sequential with interdependency. The tasks are required to run one after the other. Secondly, the output file of one task becomes the input file of the next one. By running on the same VM, we avoid the cost and the time of transferring this file in and out of the global storage. To avoid communication and processing overhead, as well as VM provisioning and deprovisioning delays, tasks in a pipeline are clustered together and are always assigned to run on the same VM. Data distribution. Task output is distributed to multiple tasks for processing. Data aggregation. Output of many tasks is aggregated by processed. As we can see here, this shows us the data aggregation and this shows us the data distribution. The unbound knapsack problem. The unbound knapsack problem is an NP-hard combinatorial optimization problem. The problem is to select the most valuable item to pack in a fixed size knapsack. The goal is to determine the number and the type of items to pack so that the total value of items is maximized. The problem can be solved using the dynamic programming. The runtime is pseudo-polynomial as it grows exponentially with the length of W. Now let's look at the algorithm. WRPS first pre-processes the DAG by identifying the pipelines and assigning deadlines to each task. To find the pipelines, tasks are sorted in topological order considering their dependency. For sorted and unprocessed tasks, algorithm recursively tries to build a pipeline for that task. Once a type pipeline is found and recursion is finished, process is repeated for the next unprocessed short task. As you can see, here we have algorithm 1 which is used to find a pipeline recursively. Line 2 to 8 shows the base case of the recursion when the processed task has no children, when it has more than one child, or when it has a single child with more than one parent task. Line 9 to 10 shows the recursive case, and at the end, algorithm will terminate if it has reached last child of pipeline. Once DAG is pre-processed, the task scheduling begins. All entry tasks that have no parent task are ready for execution. After these parent tasks finish their execution, child tasks are released onto the queue. Group of tasks into bag of task and bag of pipeline. Bag of tasks are one or more tasks that can run in parallel and have same deadline. Bag of pipeline is one or more pipeline that can run in parallel. Tasks in BOT can run in parallel, sharing same deadline and having same type, while BOP contains one or more pipeline that can run in parallel. Once BOP and BOT are created, we need to schedule them. This reflects the BOT scheduling. As we can see, the set of bags of pipeline can be done as the line 2 selects and run for each BOT. Line 3 checks task size if it's greater than 1. Line 4 decides the allocating of VMs. Line 5 select and run for every types of VMs. Line 6 select and run for every VMs of particular type. Line 7 finds minimum number of tasks. Line 8 schedules tasks in parallel. Line 9 removes BOT task, while line 10 we allocate free VM. In line 11, if VM is not available, then we provision new VM. Line 11 we allocate task on VM. As you can see, the line 8 is executed when there is one task in BOT, while line 19 single free VM for that task is allocated, while line 20 suggests that if there is no VM, then line 21 would provision a new VM. Firstly, the WRPS tries to reduce size of bag and make use of already existing VM which are idle. Wastage of CPU cycle is reduced without affecting make span. After this, resource provisioning plan is created with a goal to find the optimal combination of VMs that have combined maximum number of tasks at minimum cost of running them. VM with fastest type is least if there are no VMs that can finish tasks on time so that they run in parallel and finish early. Cost is reduced by using VM that are already paid for time slots and avoid long provisioning delays of newly leased VMs. Single tasks are basically a special cases of bags. WRPS continuously adjusts deadline distribution. Its rescheduling mechanism enables to deal with unexpected delays encountered with running tasks. Delay in one execution time affects the other tasks that are statically assigned to VM. If VM cannot finish its task on time, they are released back to the scheduling queue. BOP is scheduled using the same strategy used for BOT. The set of bags of pipeline BOP is scheduled using the same strategy used for BOT, as task pipeline have a deadline and a size. Thus, we can apply the same scheduling heuristic and the model the problem as a variation of the knapsack problem with a slight difference in the definition of the knapsack item. Finally, the WRPS shuts down a VM when the next billing period ID approaching and there are no tasks assigned to it. Now let's look at the performance. WRPS was evaluated using workflows from scientific areas like astronomy, epigenomics, bioinformatics, and astrophysics. State provisioning scheduling algorithm, also known as SPSS algorithm, assigns sub-deadlines to tasks and schedule them onto existing or newly leased VMs for minimum cost. Drawbacks of this algorithm is its inability to meet deadlines when unexpected delays occur, while WRPS succeeds. WRPS allows better quality schedules than SCS, which is a state-of-the-art dynamic algorithm which allocates VM based on current status of task. As you can see here, we are showing the make span and the deadline of the 4 workflows which are discussed in the latest slide. The main objective of all this algorithm is to finish before the given deadline. The 4 major workflows, out of them for LEGO, The difference between the make span obtained by WRPS and the deadline is marginal. WRPS demonstrates that it has adaptability and ability to generate cheap schedules by finishing its execution before the deadline with low cost and better quality. Overall, the WRPS is the most successful algorithm in meeting deadlines and accomplishing goals with static approaches fails. Here we have shown the performance for the network usage evaluation for the 4 workflows. The network usage evaluation is shown in the bar chart, which suggests the average number of files read for each workflow and algorithm. The total number of input files required by workflow task is represented by the reference line, as shown here. The WRPS successfully reduced the number of files read from the storage by 50% by scheduling pipelines in a single VM from same bags and single VM. While WRPS is not successful in reducing the number of files in ICPP workflow due to the lack of pipelines and bag of the task. To conclude, WRPS is responsive provisioning and scheduling algorithm for scientific workflows in clouds. Its objective is to meet the user-defined deadlines and minimize the overall cost. The algorithm is dynamic to a certain extent to respond to unexpected delays and environmental dynamics. There are certain components which are static attached to find the optimal schedule for a group of workflow tasks. It performs better overall than the state-of-the-art algorithms meeting the deadlines under unpredictable situation. It achieves it at lower cost than the static approaches. Thank you everyone for listening to the presentation.